Hello everyone, and thank you for joining today's webinar on efficient green energy, exploring simulation-driven design for high-torque wind turbine machines. I am Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded inside the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all the questions at the end of the presentation. Without further ado, let's jump right into it. Our agenda for today is as follows: an introduction to the fundamental concepts and principles of wind turbine electric machines. Then we will discuss the benefits of wind turbine generators offer and the design challenges they present. Next, we will delve into the intricacies of designing a high-torque, low-speed wind turbine generator, covering design specifics. Next, we will explore the EMWorks solution, simulation methodologies, and showcasing results achieved through the simulation. And at the last, we will have a live demonstration to illustrate key aspects of wind turbine electric machines and the EMWorks solution. As we all know, permanent magnet synchronous generators play a pivotal role in the world of renewable energy, specifically in the context of wind turbines and micro hydro turbines. They are favored for their efficiency, power density, and robust rotor structure, distinguishing them from induction generators and switch reluctance machines. The key advantages of permanent magnet synchronous generators lie in their design. They offer high efficiency, ensuring optimal conversion of mechanical energy to electrical energy. Additionally, they boast a high power density, packing a substantial amount of power into a relatively small space. Their rotor structure is robust, contributing to their reliability and longevity. Permanent magnet generators are typically employed in small-scale wind turbines, capitalizing on their efficiency and compact design. However, their potential is not limited to small-scale applications. These generators can also be utilized in large-scale projects reaching capacities of 7 to 10 megawatts, showcasing their versatility and scalability. Direct drive technologies has revolutionized the wind turbine industry, offering a host of benefits that significantly impact the efficiency and reliability of wind turbines. Let's dive into the advantages. One of the primary advantages of direct drive wind turbine generators is their suitability for variable speed wind turbines. This feature allows for optimal performance under varying wind conditions, ultimately enhancing energy output. Direct drive systems provide a flexible control method, ensuring a rapid response to wind fluctuations and load variations. This adaptability is vital for maintaining stable power generation and grid integration, especially in unpredictable weather conditions. Direct drive wind turbine generators exhibit low speed and high torque characteristics, optimizing their performance in the face of varying wind speeds. This trait contributes to the generator's ability to capture maximum energy from the wind. By eliminating the need of a gearbox, direct drive systems significantly reduce failures rates and maintenance costs. This leads to enhanced reliability and ultimately and also the operational expense of the wind turbine. Also, direct drive technologies alleviates stress concentrations issues that arises when supporting heavy loads, providing a more durable and resilient solution. This structural advantage contributes to the longevity and sustainability of the wind turbine generators. While direct drive generators offers numerous advantages, their design comes with a unique set of obstacles that engineers and designers need to be overcome. Let's delve into the specific design challenges. One significant design challenge with direct drive wind turbine generators is the rapid increase in size and weight due to the high torque requirements. As we aim to maximize torque efficiency, we must carefully manage this growth to avoid adversely affecting the wind turbine's overall structure and performance. Next, the weight and size of the generator must be balanced to prevent the need for costly upgrades to the structure tower. Striking the right balance is crucial to ensure the tower can effectively support the nacelle without compromising its structural integrity. Another challenge is an essential aspect of direct drive design involves optimizing air gap to handle the required flux density while preventing rotor stator rubbing under all operating conditions. Achieving an effective air gap design is critical to ensure efficiency and minimal wear and tear. Another key challenge is accommodating dynamic short circuit forces within the constraints of the minimum air gap. These forces must be effectively managed to maintain the generator's operational integrity and prevent damage, highlighting the importance of a robust design approach. So, the design challenges associated with direct drive wind turbine generators are indeed complex. Engineers and designers must carefully navigate these challenges, addressing issues related to size, weight, air gap design, and dynamic forces to create reliable and efficient wind turbine generators. EMWorks has been at the forefront of providing cutting-edge solutions for the electric machine industry. Let's explore the range of solutions that we offer. First, we have the MotorWizard tool. It is a template-based motor design software that allows users to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic, and transient solvers equipped with integrated analytical and finite element based solvers. Second, we have the EMWorks 2D tool. It is a 2D electromagnetic simulation software that uses finite elements to solve magnetic, electric, and transient problems. EMWorks 2D allows you to study the effect of the geometric or simulation parameter changes on the design. It also allows you to couple a transient magnetic study to mechanical motion and thermal. Third, we have the EMS tool. It enables a user to do both electric and magnetic simulations using complete 3D geometry. EMS is a true multiphysics software that enables users to couple the magnetic and electric design to circuit, motion, thermal, and structural analysis on the same model in a hassle-free integrated environment. Moving ahead, today our design focuses on a 3-phase scaled permanent magnet generator. Let's go over the key design parameters. The outer diameter is around 1800 mm. The stack length is 165 mm. We have chosen the number of slots as 120 and number of poles as 116. We have coil turn as 19 and we have taken the air gap distance as 5 mm. Our mechanical speed is going to be 51.7 rpm and we are going to operate the machine at 50 Hz. Hence, The total overhead rated power that we're targeting for is 50 kilowatt. So let's begin with the EM simulation and results part. EMWorks 2D interface seamlessly brings electromagnetic simulation capabilities into SolidWorks, offering an efficient and integrated environment for analyzing electromagnetic phenomena. The integration allows for easy assignment and modification of electromagnetic properties to various components within SolidWorks. This includes specifying materials, type, conductivity, permeability, and other essential properties vital for accurate simulations. EMWorks 2D interface enables precise definition of boundary conditions, ensuring realistic simulation outcomes. Additionally, it allows for setting excitation parameters and configuring circuits, facilitating detailed analysis of electromagnetic behavior. Last but not the least, let's talk about the results. Engineers and designers can analyze electromagnetic fields, current, and other relevant data, making informed decisions without leaving the SolidWorks environment. So first, let's begin with the no-load analysis. The no-load analysis involves evaluating the system's behavior when no mechanical load is applied. Our first analysis involves plotting the magnetic flux density at a rotational speed of 51.7 rpm. This plot illustrates how the magnetic flux is distributed throughout the system, providing critical insights into the magnetic behavior under no-load conditions. The second aspect of our analysis involves plotting the cogging torque versus time at the same rotational speed of 51.7 rpm. Cogging torque refers to the torque required to overcome the magnetic deterrence in the system, and this plot helps us to understand the torque variation throughout a rotation cycle. The cogging torque plot highlights the torque fluctuations, guiding us mitigating unwanted torque variation. Next, we have back EMF, which is crucial phenomena in electrical engineering, especially in motors and generators. It refers to the voltage induced in a coil when the magnetic field around it changes. And on the right hand side, we have the flux linkage, which is another vital aspect of electromagnetic systems. It is the product of magnetic flux passing through a loop and the number of turns in that loop. Here we can see the back EMF magnitude is around 220 volts, and we have a flux linkage of 0.67 Weber. Next, we will move into the onload analysis with resistive load. Onload analysis is a critical process in evaluating the performance of electrical systems under real-world conditions. First, we will specifically focus on how a resistive load impacts an electric machine. Here we can see the EMS circuit schematic with a resistive load of 1.2 ohms for all the three phases. Now, with a resistive load and observing the magnetic flux and current density in action, we gain a deeper understanding of how electrical systems behave when subjected to a real-world loads. These insights are invaluable for optimizing system design, ensuring efficiency, and addressing potential challenges. Next, we have the generated torque plot versus time at 51 rpm. A fundamental element is understanding the performance of electric machine under the loaded condition. This generated torque represents the twisting force produced by the motor, which could achieve the desired torque of 4,800 Newton meter for the design that we are focusing on today. Similarly, we can also look at the current versus time variation and the voltage induced due to the load connected across the terminal and the current induced as per the resistive load connected across the terminal. We can observe here, the moment we start our simulation, the current starts to rise and it reaches to a peak value of 120 amperes, and the voltage induced is close to 150 volt. Next, we have tooth force analysis. Tooth force analysis is a fundamental study in the field of electric motors, providing insights into the mechanical interactions within the motor. In permanent magnet synchronous motors, this analysis helps us understand the forces exerted on the motor's teeth during the operation, as you can see in the images right hand side, contributing to a deeper comprehension of the motor's behavior and efficiency. Within tooth force analysis, two primary components of interest are the radial forces and the tangential tooth forces. Radial tooth force act perpendicular to the tooth surface, while tangential tooth forces act tangentially to the tooth. As we can see here, the radial forces peak is around 120 Newton meter for the design that we are considering today, and on the right hand side we have the pictorial representation of the tooth forces acting on the stator tooth. Next, we can also look at the winding loss analysis, which is another crucial component. First, the total winding loss plot versus time, which is on the left hand side. This graphical representation showcases how the total winding losses occur over a time. By examining this plot, we can glean insights into how these losses evolve, aiding us in optimizing the system. And on the right hand side we have winding loss density, which is a dynamic representation that provides a deeper understanding of the distribution of losses across the winding. And we can see here the losses occurred is the peak value is around 1.3 watt per meter square. This allows us to visualize how losses are distributed within the winding structure. Next, we will look at the different series of experiments that we conducted. We varied the speed from 51.7 rpm to 70 rpm and next 100 rpm. And for this effect of speed variation, we'll be focusing on the results of torque plots and the winding loss plots, and we'll shed light on how the speed alterations affect these critical parameters. If you look at the torque plots for the different speeds, the torque is a critical parameter and it has a direct effect on the machine's output and performance. By examining the torque plots at these speeds, we aim to understand how the torque generated varies with rotational speed. And similarly, if you look at the winding plots, which is like winding loss plots at the specific speeds, we can observe that these losses changes with the varying speeds. Next, we can also have a complete core loss analysis. It involves evaluating the losses that occurs within the core of machine. Here we can easily segregate the total core loss into the core losses and into like various components such as the eddy current losses and the hysteresis losses, as well as the excess losses. And we can see the losses in both the component, in the rotor as well as in the stator. Next, similarly we simulate the machine with RL load. As you can see here, we have connected 0.5 ohms and 1.8 nanohenry of inductor and resistor. The plot center involves a dynamic graphical representation that displays changes in the magnetic flux density. Magnetic flux density represents the amount of magnetic flux linkage within a given area, and on the right hand side we have the plot which depicts the torque generated by the system as a function of time, especially at a rotational speed of 51.7 rpm. Next, we'll analyze and visualize how temperature is distributed across both the stator, which is on the left hand side, and the rotor of the electrical machines. The winding losses usually occurs due to the resistance in the wires, which contributes to heat generation. We can observe that due to winding losses, the stator core temperature is around 121 degrees Celsius, and for the rotor it goes up to 37 degrees Celsius. Next, we will examine how temperature induced stress affects the structural integrity and performance of the stator. By evaluating these deformations, engineers gain crucial insights into the material's behavior under varying temperature conditions. So this understanding plays a critical role in designing robust systems capable of withstanding thermal stress and maintaining optimal functionality even when subjected to extreme temperature variations. So here we can see the deformation that occurred is close to 200 micrometer, which is not big enough for the size of the machine that we are designing today. But of course, this deformation could affect if based on your application and the outer diameter of your motor. So far we have obtained the performance analysis of high torque, low speed permanent magnet generator using the EMWorks 2D software, where we observe its on-load analysis and no-load analysis, such as back EMF, cogging torque, electromagnetic load torque, and the losses, whether it's a hysteresis loss, eddy current loss, or the excess loss. We also use the EMS software to get its thermal and structural analysis. Now, once we know the D-axis and Q inductance parameter from the previous simulation, and or either from the software, or you can use from any other third means to get this parameter, we can use these magnitudes to further analyze and get performance of the motor without the need of geometry, and that's done using the performance calculator, which is one of the feature of our MotorWizard tool. So moving ahead, here we have obtained the D-axis, which is here, and the Q-axis inductance as for the machine as in the motoring mode, and we can see how inductance value decreases as we increase the current. Therefore, using the MotorWizard tool, a user can feed in the parameters such as flux linkage, D and Q axis inductance, the rated current, and the speed of the machine, and can quickly get the efficiency map of the machine within a seconds. And next we have the motor versus torque speed as shown in the figure on the right hand side. So here is a quick demonstration which shows how a MotorWizard tool can be used to quickly generate the performance curve. So once we are into the MotorWizard tool, we will select performance calculator. We have selected the brushless permanent magnet motor, and we need to enter this equivalent circuit parameters as shown in the previous slide, the core loss parameter and the operating parameter. Then we go to calculator section and select the performance and click on the calculate to obtain performance results. So let us look at the voltage versus speed curve. So we have a D and Q axis voltages. Then we can also obtain the D and Q axis current and the torque versus speed of the machine, also the power versus speed, and finally we can obtain its efficiency map as shown here. And user can also obtain the magnitude of efficiency at different points by just clicking or using its cursor on the map. So to conclude today's webinar, EMWorks offer a holistic suite of tools encompassing both 2D and 3D dimensions, providing a comprehensive solution for the analysis of electric machines. This toolkit covers electromagnetic properties, structural aspects, motion dynamics, and efficiency analysis, presenting a versatile platform for in-depth exploration. Leveraging EMWorks tools for virtual prototyping and scaling proves to be an efficient strategy. Particularly, it facilitates the thorough investigation and assessment of wind turbine generators designs, especially those deployed in substantial megawatt. Applications ranging from 7 to 10 megawatt. This approach offers a valuable avenue to optimize design parameters and enhances performance. The analysis of a specific wind generator prototype using EMWorks tools shed light on crucial aspects related to high torque and low speed machines. This prototype serves as a valuable model for studying phenomena intimately connected with such machines. It provides insights into challenges like significant loss accumulation and concentrated forces stresses, offering a solid foundation for further research and design enhancements. So here are the references for our today's webinar, and now the floor is open for a Q&A session. Thank you everyone for attending today's webinar. Thank you.